All right, so let's finish up section 4.2. I'm going to compare it to what we did yesterday first. So yesterday, okay, you don't have to write that down. This is what we did yesterday. We looked at graphing problems where the degree in the top was either smaller than what was in the bottom or equal. Okay, that's what we did yesterday. Yep.
Wow.
Now, that's what we're going to do today. We're going to look at graphing problems where the degree in the top is bigger. So when the degree in the top is bigger, different things can happen. We'll see what ends up happening, but it can change your asymptotes. Instead of just getting an asymptote that's horizontal, because we're still going to have the verticals. Okay, that's not going to change. But instead of having an asymptote that's horizontal, we might get an asymptote that's on a slant. So it's still a line, but now it's kind of on a diagonal. Or if the degree changes even more, we can get an asymptote that has a curve to it. So not the graph is curved, the actual dotted line, the asymptote in the graph is curved. And those can get a little tricky. So we're not going to look at ones that are like crazy curves. The highest we'll probably do is a parabola, but it could be anything higher than that in general. Okay, but we're not going to look at things that high. All right, so when the degree in the top is bigger, there's this thing we didn't talk about yesterday. We talked about an end behavior model. That's just when you take the highest degree term in the top, divide by the highest degree term in the bottom. Well, when the degree in the top is bigger, there's this new thing called an EBA, okay, end behavior asymptote. And the end behavior asymptote, you already know how to find it. Now, we never called it this before, but last week I taught you something that will, if you remember it, will enable you to find the end behavior asymptote. All right, so if you divide h of x by g of x, that's a rational function. Okay? And just like all the problems we did yesterday, h of x would be a polynomial, g of x a different polynomial. When you divide them, you're going to get a quotient, and you're going to get a remainder. Okay, I can't just say the quotient is a number and the remainder is a number. It might not be a number. Sometimes the quotient has letters in it. Okay? If you just divide numbers, then you only get numbers in the quotient. But when you divide things with letters, sometimes it has a letter. Okay, so q of x is the quotient. R of x is the remainder. Well, last week we saw this formula. F of x equals your quotient plus your remainder over your divisor. And if you don't exactly remember that, I'll show you a quick example with numbers. Let's suppose I said 2 equals 10 divided by 5. I just filled in numbers for f, h, and g of x. Just numbers, no letters. Okay. I need to write down here, what's the remainder when you do 10 divided by 5? 0. There's no remainder in this case. So just pick something simple. And the quotient, when you divide 10 by 5, what do you get? 2. Okay, let's plug those numbers into the formula and see what happens. Right. So if I look at my quotient, which was, I'm just going to write it over here, 2, plus my remainder, in this case it was just a 0, over my divisor, which was 5, that should equal the original thing I started with, which was 2. Right. Does that work? Yeah. What I started with equals my quotient plus my remainder over my divisor. If it didn't work, like, let's say when you divided this, you accidentally made a mistake, and you said, all right, 10 divided by 5 is 3. Well, if you try it now and change your quotient to 3, it doesn't work. So what that means is this is a way to check your division, and it shows you did something wrong. All right. So that's all that this formula is. It's a way to check your division. But the important thing in the formula is just that right there. Q of x is what you call the end behavior asymptote. So the EBA is just the quotient. And we did that last week. We didn't call the quotient an EBA, but that's what it is. So to find the end behavior asymptote, just do the long division and then write down the quotient. That's it. Now you have two ways you can do the division. You can do long division, or what's the other way that is faster? Synthetic, but you can only use it if the denominator is x minus a number. If the denominator is more complicated than x minus a number, you got to do long division. Okay. So what's the difference between the quotient and the EBA? They're the same. There is no difference. So if a problem asks you for the quotient, if a problem asks you for the EBA, they're asking you for the same thing. Yep. Okay. So this problem says find the quotient, the remainder, and the EBA. How many different things is this problem really asking you for? It's only asking you for two. The quotient is the EBA. So once you find that, that's both of them. The remainder, well, that's different. So we could do this one with synthetic. We're not always going to be able to use synthetic. So do people want me to do it as synthetic or do it as long division? Long division, okay. So you're going to have to use long division. That always works. It's just it's not the fastest for this one. All right, so x minus 2. Before I write down what's going to go under that symbol, I'm going to have to fill in a 0 for what term?
X.
The x term.
Wait, why can't we do synthetic?
You could.
Oh, okay.
You could.
We wanted long division.
Yeah, somebody didn't want to.
Oh, okay.
Sorry. Duh.
But the long division is good to practice because it always works. Okay, synthetic division doesn't always work. All right, so I got 2x cubed divided by x. Mallory, what's 2x cubed divided by x?
2x.
Yep, 2x squared. Multiply it back out. You get 2x cubed minus 2x squared. And then what do you do with those columns? Subtract them. If you're doing long division, you subtract. If you're doing synthetic, you're going to add. Is that what you're going to mention, Ian? Thanks. So multiply it back out. Make sure you multiply correctly. 2x cubed minus 2x cubed. That's gone. We have negative 4 minus 4.
So negative 8 x squared.
Well, it's like negative 4 plus 4.
So 0.
0. So this cancels out. At this point, because the next term is 0, not much interesting is going to happen. If you take 0x and divide by 0, you just get 0. But we need to keep going because they asked for the remainder. So now multiply the 0 back out. What's 0 times x?
0x.
It's just 0x. What's 0 times negative 2?
0.
Just 0. And now if you want, you can bring down the next term because that's what you're combining it with. Subtract. 0 minus 0 is 0. What's 3 mince 0? 3. So it's not really necessary to go through all those steps at the end if you can just see the remainder is 3. All right. So what do they want to know? Quotient, 2x squared. Remainder, 3. What else? EBA. What's the EBA? 2x squared. And we're going to use this problem. This is going to be the first graph we draw. Okay? We just found the end behavior asymptote of our graph. What shape is x squared? It's a parabola. So when we sketch this, we're going to have an asymptote in the graph that's going to look kind of like that. So you might be like, well, how can you have that? Well, maybe our graph is going to do something like this. And it's just going to get closer, closer, and closer. So maybe the graph looks like that solid line. And it's just going to get closer and closer and closer to it. Okay. I don't know. We'll see when the graph's. Any questions on how we got, especially the EDA? Again, you could have used synthetic, which would have been faster. All right, so let's do this. Okay, so we're throwing around a lot of different terms, okay, between yesterday and today. And there's a difference between the end behavior model and the end behavior asymptote. The end behavior model, that's what we did yesterday. That's easy to find. Just take the highest degree term in the top, divide by the highest degree term in the bottom. The EDA, that's a little longer to find. Okay? The EDA is when you have to do the long division, or synthetic division. Okay? So there's a difference between the two. Also, the EDA doesn't even exist for the kind of problems we did yesterday. There's no such thing. Okay, the only time you have an EDA is when the degree in the top is larger. And we didn't do that yesterday. Okay, if you had a problem like we did, the one we just did, I could have asked you for the EBM. If I go back and look at it, the EBM of this problem would be take the biggest term in the top, 2x cubed, divide by the biggest term in the bottom, x. So the EBM for the problem we just did is 2x squared. In that case, it happens to be the same as the EBA. So sometimes the end behavior model and end behavior asymptote are the same. Sometimes they're different. It depends on how the problem is set up. In the kind of problems we did yesterday, okay, the degree of the numerator was always less than or equal to the degree of the denominator. All your asymptotes are straight lines. Okay, you might have some vertical ones. We're still going to have vertical ones today. But we have vertical ones and you have horizontal ones. Well, if that's not true, okay, if the degree in the numerator is larger, you might still have vertical. Okay, that all depends on if the denominator can equal 0. But when the degree at the top is larger, you don't have horizontal anymore. Okay? You can get asymptotes that are on a slant. That's like the next step up in difficulty, slanted asymptotes. And then even another step up from that is curved. Like the last problem we just did, that's curved. Okay? It was in the shape of a parabola. Okay? So kind of problems we did yesterday, you're always going to have your verticals. You could also have a horizontal. The ones we're doing today, you're still going to have the verticals, but you're not going to have a horizontal. That's either going to be replaced with a slant, which would be one step harder, or something that's curved. That would be 2 steps harder. We'll do one of each. One that's a slant, one that's a curve. And when I say curved, it could be any kind of curve. It could be a parabola, it could be a cubic. It could get really pretty bad. But I told you I'm not going to give you anything worse than a parabola. And how bad the asymptote gets, you can tell just by looking at the original problem. Okay. If you look at f of x, what's the degree in the top?
3.
3. What's the degree in the bottom?
1.
1. What's the difference between 3 and 1? 2. So there's a difference here of 2 degrees. That's what the end behavior asymptote is going to be. It's going to be a degree 2. If the top was a degree 4 and the bottom was a degree 1, that's a difference of 3. So you'd have a cubic end behavior asymptote. So the further apart the degrees are, the worse it gets. It's not just if they get bigger, because if the top was a degree 5 and the bottom was a degree 3, that's not bad. Degree 5, degree 3, that's a difference of 2. Okay? So that's what you look at to see how bad the EBA is going to be. What's the difference in the degrees? All right, let's. So if you look at that one real quick. Degree 3 in the top, degree 1 in the bottom, what's the difference?
2.
Degree 2. That's a parabolic asymptote. What's the degree on that one in the top?
3.
3. What's the degree in the bottom?
2.
What's the difference between 3 and 2?
1.
1. That's going to be easier because there's only a difference of a 1 degree. Okay. So that one will be harder. All right, so let's look at a picture of the graph from example 5. And let's verify what we just found. Let's show that 2x squared really is the end behavior asymptote. Okay, I'm going to do a couple things here I haven't maybe shown you on the calculator. I'm going to change the color of the line. I'm also going to change the thickness of the line. Because when you draw things thinner on the calculator, it's more accurate. Okay, because the resolution on the screen is not the best. So I'm going to draw the graph a little thinner. All right, so let's type in what we had in example 5. So we have 2x cubed. Actually, I think it's on the next page. 2x cubed minus 4x squared plus 3. Right, so start with that. So 2x cubed minus 4x squared plus 3. And then it was divided by x minus 2. Okay, I'm going to, let's see. Well, we can leave that as a blue line. That's just the color it's going to be. But I want to make it thinner. Okay, and the way I can make it thinner is to highlight the box you see blinking. Hit enter. Go down a line, and I can choose different styles. If I press left, I don't know if you noticed, but it got a little thinner. And then go to OK. So it's going to just make it a thinner line. And now I'm going to graph the EBA, which is 2x squared. I'm going to do the same thing. I'm going to make it thinner. I'm also going to make it dotted, because we usually make asymptotes dotted. All right, so highlight it. Dotted. Okay, there's 2 dotted. There's a thicker one and a thinner one. Just go with the thinner one. Okay, for your window, let's set the Ymax at like 40. Okay, you can keep everything else the same, negative 10 and 10. Okay, so set, I'll put this on here so you can see it. Set that as your window. And that's what you want to type in for your graph. Okay, let's graph it and see what we got. So that's the graph. And what it's going to draw in red in a second is going to be the asymptote. All right, it's a little hard to see, so let me make it bigger. All right. Can people tell? I don't know if you can really tell, but if you look at this blue section and then look at those red dots right next to it, can you tell that the red dots are getting closer and closer to the blue line?
Yeah.
Yeah. So what we've shown is that that is the asymptote. Same thing here. You've got the red dots going up, you've got the blue line going up, and the red dots and the blue line are getting closer and closer and closer, till finally it looks like the red dots are right on top of the blue line. Remember, they're really not, but I can't draw the line any thinner than that, so that's the best I can do. All right, so we've done what they wanted in example 5, or example 6. Use the graphing calculator to show that what you think is the asymptote actually looks like an asymptote, and it does. Any questions on that? So when you have to sketch something that has a parabolic asymptote, you basically sketch that red line. That's how I start. And then I know I'm going to have a problem at what number? What number are you not allowed to plug in for x here? 2. Because if you plug in 2, you would divide by 0. So my graph is basically going to look like a parabola, but at 2, it's going to do something weird. So what I do is erase the section around 2, and then I start figuring out, how does it look? But when you start to get away from 2, the red dots and the blue line are basically going to look exactly the same. They're just not going to look the same near 2. Okay, you got to figure out what's happening there. Okay. So let's see if we can make a sketch. So in example 5, we already figured out the EDA. Okay, so if I wanted to sketch this, that's the first thing I would do, find the EDA. We already have it. Okay, so what I'm going to do is I'm going to sketch the parabola 2x squared. How do you sketch it? Just pick some values for x and plug them in. Let's do 0, 1, 2, 3. I don't think I can go any higher. If I do, it's going to go off the grid. Okay, on my y-axis, I'm going by 2's, okay, to have a little more space. All right, if I plug in 0, Josh, what's 0 squared times 2?
0.
0. Okay. So 0, 0 is a point on the parabola. 0, 0. Gabby, what if I plug in 1? What's 1 squared times 2? 2. And because of symmetry with a parabola, that's also a point. Okay, if you plug in -1 and square it times 2, you still get 2. Mike, what if I plug in 2? What's 2 squared? 4, and then times 2? 8. So we get the point 28. And -2, -8. And let's do 3. 3 squared is 9, times 2 is 18. So 3, 18, and also -3, -18. Okay, so I'm going to draw that as a parabola. What I can do is I can make it dotted after I draw it. So, let's see. Okay. So that's my EDA. Okay, make it dotted because it's an asymptote. And now let's figure out our vertical asymptote. Okay. Set the denominator equal to 0. Okay. What's the vertical asymptote here? 2. So we're going to sketch a line, a vertical line at 2. All right, so let me put in a vertical line at 2. Okay, so those are my boundaries. Now, I know my graph isn't going to be a connected parabola. It's going to be very, very close to it as you get away from 2. But near the section that's 2, I basically want to erase that, but leave my numbers if I can. Okay. Erase the section near 2 because it's not going to connect. This parabola is going to be broken into 2 pieces, and that green line is what breaks it into 2 pieces. All right, now what I'm going to do is go to my table. Okay, I've already got it typed in. And I'm going to plug in 0, 1, 1.99, just to kind of see what's happening. So if I plug in 0, I'm at negative 1.5. Remember, my y-axis goes by 2's. So negative 1.5 would be about right there. Let's try 1. 1, negative 1. So over 1, down 1. Okay, remember, it goes by 2's. Okay, let's try 1.99. Negative 3,000. So as I start to get really, really close to that green line, all of a sudden my graph just drops. All right. So basically what's going to happen in that section is as you move away, you're going to be right on top of that dotted line. You're going to start moving away from it. It's going to curve. And then it's going to start getting very close to it again. That's about how it should look. Now we got to check what's happening on the other side. On the other side, you're basically going to be trapped in that section right there. The green line is going to bound it on the left, that black curve. Remember, that was part of our parabola. That's going to bound it on the right. So what I'm going to do is I'm just going to check a couple points. I'll check like 2.01, maybe 2.5, and then I'll check 3. Okay, just to get an idea of where I am. So let's check 2.01. Okay. Just after 2, I'm way up at 3,000. So my graph is up very, very high. Let's check 2.5. At 2.5, I'm at 18.5. So about right there. And that's pretty much all I need. Okay, I know I'm trapped in that section, so what's going to happen is it's going to kind of draw it. Kind of come down at some point, hit the bottom, and then curve and go back up, always staying between the green and the black section. Okay, let's look at that with a window exactly like I have here. Set your y-max at 20, which is what's on my grid, and all you're going to see is a little tiny U in the very, very top of the graph. That's going to be your sketch. Okay, so there's the left side. That looks pretty good. And then you can just barely see it right there. If you set your y-max up to like 50 or 60, then you see more like what I drew. You start to see more of it. Okay? And that's the toughest one we do today. Okay, all the other ones are going to be much easier than that one. Okay, any questions on how we sketch that? Okay, so it takes a little practice to get used to them. But remember, you get your calculator, so you can kind of use that to help you. But the steps are sketch your EBA, erase the part that's near the vertical asymptote, and then use your table. You've got to use the table and check a few different values. Check values very close to the asymptote on each side. And then if you're still not sure, check a few more values, like I did. Check 0, check 1. And that's how you do it. Okay, so again, that's called a parabolic asymptote. Let's see if I have. All right, let's try this one. This one's going to be a little easier. Okay, what's the difference in the degree between the top and the bottom here? It's only 1. So your asymptote is going to be a degree 1. What's a degree 1? A slanted line. So you're going to just have a dotted line that's slanted. Not as bad as a curve. And this is the kind of problem I would probably expect to see on a test. It's not as easy as a horizontal asymptote, but it's not as hard as the one we just did. It's kind of in the middle. So it's a pretty good one. All right, let's start with, let's just do it in the order they asked for it, the EBA. How do you find the EBA? Long division. Why not synthetic?
Because it's not lower.
Right, it's not x minus a number. You can't use synthetic here. They don't ask for the remainder either. So once you have the quotient, you can stop. So let's find that. Okay, fill in a 0 for anything you're missing. 2x cubed. 7x squared. What do we fill in for the x term? 0x. Minus 4. All right, what's 2x cubed divided by x squared? Yep, 2x. Okay, multiply it back out. Make sure I do it correctly this time. 2x cubed, 4x squared, minus 6x. And what do we do with those columns? Subtract. So subtract. What's 2x cubed minus 2x cubed? 0. What's 7x squared minus 4x squared?
3.
And 0 minus, or 0x minus 6x. 6x. And you can bring down the next term. It's not going to really matter unless you want the remainder. So the last thing we have to do, and then we can stop for the EBA, what's 3x squared divided by x squared? 3. There's your EBA. If you want the remainder, keep going. Distribute out the 3 and keep going. So it's 2x plus 3. Okay, remember when you graph a line, start with the y-intercept. Okay. What's the y-intercept here? AJ? 3. So put a dot on 3. And then what's the slope? 2 over 1. So rise 2, run 1. Up 2, over 1. Up 2, over 1. Do it as many times as you need to. And for your EBA, that's it. So it's not as bad as a parabola. That's our EBA. And it's a slant. In fact, it's called a slant asymptote. And I'll mention that in a second. Okay, so that's a slant asymptote. All right, what else do they want? Vertical. Okay, how do you find your vertical asymptotes?
Difference.
Vertical asymptotes have to do with what you're not allowed to do in this fraction.
So I can take the denominator and do something.
Do something with the denominator, yes.
So you can't divide by
Set it equal to 0. Yeah. X squared plus 2x minus 3 equals 0. When you solve a quadratic, your options are factoring or quadratic formula. Those are the two most people pick. If it factors, that's faster, and this one does. So x and x, two numbers that multiply to give me 3, and subtract to give me 2. Positive 3, negative 1, let's double check. X squared minus x plus 3. X is plus 2. Everything looks good. So, what would make the first factor 0? Negative 3, and 1. Okay, so put a vertical line at negative 3 and 1. So, this is going to look more like the ones we did on yesterday, okay, where we had the horizontal and the 2 vertical, so it was broken into 6 sections. Well, same idea here, except we have a slant with 2 verticals. Okay, but it's still going to be broken into 6 sections. Okay, let's put in our verticals. Negative 3 and positive 1. Okay. So now the rest of the problem is just using your table. Use your table and find some points on each side of the asymptote. And then check one on the edge of your graph. Check negative 10. Check, well, whatever I go up to. Positive 8 or 9 or so. All right, so let's type it all in. And see what we got. So we got 2x cubed plus 7x squared minus 4. So plus 7x squared minus 4. If you have the last problem typed in, you can just change a few things and that works. So it's x squared plus 2x minus 3. All right, my first asymptote is negative 3. Can someone give me a number that's just a little smaller than negative 3?
2.4.
Smaller, so to the left.
Negative 2.99.
That would be bigger.
Negative 3.1.
Negative 3.01.
Wait.
Yeah, remember with negative it's reversed. So negative 3.01, just a little smaller than negative 3. You're way up at 120. Way up there. Okay. What would be a number that's a little bigger than negative 3?
Negative 2.9.
Yep. Negative 2 point, I'm going to go even a little closer, 2.9. So when I'm to the right of negative 3, I'm way down at negative 1200. Way down there. Okay, let's check positive 1. That's my asymptote. What's a number that's a little smaller than 1? Oh, Kelvin?
0.00 or
a little smaller than 1.
0.009, right?
That's a little bigger than 0.
A little smaller.
A little smaller than the number 1. Like just before 1.
Oh, then 0.9.
Yeah, like 0.9, 0.99, somewhere around there. So if I, just before 1, way down. Okay, number a little bigger than 1 would be, it's a little bigger than 1.
1.01.
1.01, perfect. Way up. Okay, now I'm going to check negative 10, because that's just a point on the edge of my graph. That's the only reason I'm checking it. Negative 10, I'm off my graph. Let's check negative, let's try negative 5. That's on my graph. So negative 5, I'm at negative 6.5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6.5, about right there. All right, so in the left section, it's going to look like this. Very close to that dotted line. It's going to start moving away from it, but then it's going to be trapped by that other one. Okay, in the right section, it's kind of like the parabola. It's going to be trapped in that section right there. Right. So it's going to come down, it's going to curve, and go back up. The only thing I don't know what's happening is in the middle. I know it's doing something like that, and something like that, but what would be another good value for x I could plug in? Just to maybe get one more point in there.
Negative.
0? Yeah, that'd be a good one. What else? 2 would be outside that.
-1.
Yeah, -1 would be good. So we go through the point 0, 1.3.
Oh.
All right, and I could check -1. -1, -0.25. Okay, so I think I got enough points. I can see what's happening. It's going up. It starts to move away from that one, but then it's trapped by the slant. Okay, it wants to keep going, but then all of a sudden it's going to hit another one, and it has to come back down. Okay, let's look at our graph and see how we did. Keep in mind, on a standard window, you're just going to see a very little small U in the upper right-hand corner. Okay, you're not going to see very much. Let's see how we did. So there's the left section. That's the middle. And there's that little U I was talking about at the top. So there's your graph. Any question on that one? Okay, so not quite as easy as the horizontal, not as bad as trying to sketch something with a parabola. It's in the middle. So that's probably a good one for the test. Okay, and that's called a slant asymptote. Okay, any question on anything we did there? Yeah?
Would you get the polynomial for the vertical asymptote?
For the vertical asymptote, we took the denominator, set it equal to 0, and then factored it. So that x squared plus 2x plus 3, or minus 3, that was in the original problem.
Okay.
Yep. So that would always be given to you. Anything else on that one? All right, so let's, this one, we're just going to look at on the calculator. Okay, before I graph it, what kind of asymptote would you expect to see here for the end behavior asymptote? Yeah?
Curve.
You think it would be curved? How come?
Slant, 'cause
Look at the highest degree term in the top, look at the highest degree term in the bottom, and figure out how far apart they are.
The
Yep.
highest degree on the top is 4, and the bottom is 3.
Top is 4, the bottom is 3. What's the difference?
1.
1. That's exactly what we did last time. Difference of 1. So you're going to see a slant asymptote when you graph it. Okay. Other than that, I'm not going to say anything else. I just want you to graph it and see what happens. Okay. And this is going to emphasize the point of looking for things that are hidden. Something that might look obvious, but it's really not as obvious as it looks. So we got 2x to the 4th plus 7x cubed plus 7x squared plus 2x. And divided by x cubed minus x plus 50. Okay, I'm going to start with standard window. Just do zoom 6. Okay, I can kind of see a slant asymptote, maybe somewhere in there. So I'm guessing if I zoomed up a little further, this top part would probably start to curve a little. So my slant is probably in there somewhere. All right, but just looking at that graph, is there anything about it that looks a little suspicious? Something we might want to check out a little more? Yep.
The bottom.
The bottom? Well, I think if you zoom out or you check what's happening on the bottom, I think you're going to see that just keeps going that way, and that keeps going that way. So basically, all you'd see if you zoom out is something like that, and something like that. don't think you're going to see too much more there. But there's something that's actually on the screen we need to check out more. Okay, not something that's off the screen. Yeah?
The bottom of the two, it looks like it doesn't connect.
Yeah, down in, you're saying like down in here?
Yeah, in that area down there, it doesn't look like it connects in there.
All right, let's zoom into that box. Set your y min at -1, y max at +1, and then set your x's. So -3 to +2, and -1 to 1. So now what I'm going to do is I'm basically blowing up that section that's in the black box so it takes up the whole screen, and see what happens now. Let's speed it up a little bit. Okay, can we really see anything more from that?
It looked like it stopped, but you can't really tell.
Well, yeah, it kind of looks like if we
I can't see.
let's put this over here. Right, if you make it maybe a little bigger, kind of looks to me like something's happening there. Like maybe it's going down and almost coming back up again. Okay, I can't really tell. So let's zoom in again. This time, let's set our y min and max. So basically, we're looking at this. Let's set it like -0.1 to 0.1. So let's zoom in 10 times as much. And we're going to start to see what looked pretty flat at first. Well, you'll see. Okay, so this is the same graph, just zoomed in even more. Okay, so what looked like it was pretty flat, now you can tell it wasn't flat at all. Make it bigger.
So that's
Okay.
on a 4.
Yeah, that's because it's actually crossing 1, 2, 3, 4 times.
Alright.
So on a graph like this, I could ask you, how many times does it cross the x-axis? And if you just look at the original, I can't really tell at all. Even zooming in a little bit, I still can't tell. I had to zoom in even more. I could also ask you, does this graph have a local minimum? And you'd say, yeah, it has 2 of them. Local minimum is a point that dips down. Does it have a local maximum? Yeah, that's a point that's higher than everything else around it. Right there, it's like a little hill. That's a local maximum. Again, looking at the original or even the zoomed in, I can't tell. I have to zoom in twice. All right, so just a reminder about, make sure you zoom in if you can't really tell what's going on. And sometimes you have to zoom out. It all depends on the problem. Any questions on that? All right. So the homework tonight, it's the same page, same section as last night. It's 235, 40 to 43. That's all. 45 to 47, all. And 51 and 55. Just as a reminder, I will be after school tomorrow for extra help. If you need to make up a test, tomorrow is the last day to do it after school. Other than that, you have to get it done on the day, during the day Friday.